So this lesson covers some material from Unit 910. We're still looking at rates of change, limits, and the derivative, but now we're taking a closer look at limits and limiting values. And what we want to cover in this lesson is, by the end of it, we want to know what do we mean by a limit. And we already have kind of an understanding of what limits are about. In our first lesson, we looked at some stuff that you did back in advanced functions about finding the instantaneous rate of change using those tables. And we said that was kind of like taking a limit. And then we developed that in our next lesson on the tangent problem, where we actually sort of formalize that method of finding the slope of the tangent by taking the limits of successive slopes of secant lines to our function. Okay? So we want to really nail down this concept of what a limit is, and in particular here we are going to look at how we evaluate limits using tables and how we evaluate limits using graphs. And in our next lesson for the material in Box D, we're going to take a look at how you can evaluate limits algebraically. So what we've been saying all along is that if we wanted to evaluate a limit, we kind of set up this table and we looked at the trend that the numbers were heading towards. So the limit wasn't any particular number in our table, it was the trend that the numbers were heading towards. If we want to make this a little bit more formal, we can put up this mathematical statement that I've kind of been using here. Limit as x goes to a of f at x is equal to L. And L is just some number here. And it's always got to be a number, in fact. It's the number that all of our successive approximations seem to be heading towards. Okay? And that number is what we call the limit. Okay? So the limit of f at x as x approaches a is this number L. And what does this mean? What it means a little bit more formally mathematical. When you get to university, you're going to see the real formal definition of a limit here. But really what this just means is that as we make our value of x closer and closer to some number a, the value of f at x, or a function, is going to get closer and closer to this number L. Okay? And again, a is just some number as well. Okay? So this kind of goes back to those concepts of independent variable and dependent variable that you started talking about back in grade 9. X is always our independent variable. We can change, we have control over it. So we can take the value of x that we're using and we can change its value. And if we move it closer and closer and closer to some number, a, it doesn't actually have to be equal in value to a. We know that the value of our function, f at x, that we can calculate using those values of x that we're changing, is going to get closer and closer in value to some other number. And if that is the case, we can say that that number, L, is the limit of that function as x tends to a. And as we've already talked about, we can evaluate limits in a number of different ways. We are going to look specifically here at tables, and we're going to look at graphs, how we can interpret limits if we've got a graph of a function. And then eventually, the one that you're going to use most often is probably how you evaluate them algebraically. But again, that's for the next lesson, topic D. Okay. So the one that we're kind of familiar with now is this table approach. So let's take a look at a limit that we can evaluate using tables. So the function we have here is 3x squared minus 3 divided by x minus 1, a rational function. And we want to evaluate the limit as x tends to positive 1. Okay. So I've set up my two tables here. I've got a column for x, a column for f at x, and I've got, well, two columns for x and two columns for f at x. Because what we're going to do here is we're going to evaluate this limit from both sides. Okay. We talked about this a little bit before. We talked about evaluating this thing sort of from the left, okay, which means we are going to start approaching that value of x equals 1 from values of x that are less than 1. And we're going to also evaluate this over here from the right, which means we are going to approach, we're going to make our x values approach positive 1 from values, using values of x that are greater than positive 1. So the way we would write this, approaching from the left or approaching from the right, is we're evaluating the limit as x tends to 1. If we mean that we're approaching from the left, we put a little minus sign up there, okay? So x is approaching 1 from values of x that are less than 1, and our function again is 3x squared minus 3 over x minus 1. And we're going to find out what number all of these things tend towards. So this is a straightforward procedure here. We pick values of x that are getting closer and closer to x equals 1. So I might choose something like 0.9, 0.99, 0.999, 0.9999, and then I would just take these x values and I would sub them into my function, 3x squared minus 3 divided by x minus 1. A little bit of calculator work and I see what I get. So what I get is 5.7, 5.97, 5.997, 5.9997. So if you look at that second column of that table, what is our limit here? What is the value that these f at x approximations tend to be tending towards or heading towards? Shane? 10 to be 6. So we can say that the limit as x approaches 1 from the left of 3x squared minus 3 over x minus 1 is equal to 6. And then we're going to do the same thing approaching from the right. So we're going to take the limit as x approaches 1. Little plus sign there means we're approaching from the right, or from using x values that are larger than 1, of 3x squared minus 3 over x minus 1. So we pick some x values here that are a little bit bigger. So 1.1, 1.01, we're making them smaller here so that they're getting closer and closer to 1. 1.001, 1.0001. And again, just plug them into our function and evaluate. My calculator says 6.3, 6.03, 6.003, 6.0003. So looking at that second table, what is the limit as x tends to 1 from the right of our function? 6 again. Is this good? As we approach from the left, we tend to be heading towards 6. As we approach from the right, we seem to be heading towards 6. So our two tables are kind of in agreement here, that this is what we should be heading towards as we get closer and closer to what our function is heading towards as we get closer and closer to 1. So we can put these two things together and say, therefore, that wasn't a very good therefore, therefore, the limit as x tends to 1 of 3x squared minus 3 all over x minus 1 is equal to 6. Now, you might be asking yourself, that's a lot of work. Why don't we just take x equals 1, stick it into our function, and evaluate it? That'll tell us what the value of the function is at x equals 1. What happens when we do that? F at 1 would be 3 times 1 squared minus 3 all over 1 minus 1. What do we get up in our numerator, Liam? What do we get down in our denominator? Right. What is 0 divided by 0? I don't know what 0 divided by 0 is. I know it's bad news when I'm dividing anything by 0. I know it's doubly bad news when I'm dividing 0 by 0. I know that it is definitely not equal to 6. What's going on here? Turns out that this is a function that isn't actually defined at x equals 1. It doesn't exist at that point. But the limit, as we get closer and closer to 1, does exist. So you get these weird little cases where the function doesn't exist at the point where you're trying to find the limit, but the limit to the function does exist at that point. Okay? So there's a difference between the value of the function and the limit as we approach a particular x value of that function. And we're going to take a look at what that looks like when we look at some of these graphs here. Okay? So let's move on here and actually take a look at how you would evaluate a little bit more straightforward limits using graphs. So let's imagine we've got a function here. F at x equals 1/2 x squared minus 4. This is a nice little parabola, opens up. We know that because the sign of the leading term is positive. It's got a vertex down here at 0, -4. And we want to use this graph to evaluate this limit. The limit as x tends to 2 of our function, 1/2 x squared minus 4. Just to emphasize that this goes off to infinity here. So we want to figure out what happens if we are heading towards a value of x equals 2, right there. So we imagine starting a little bit away from it. I'll switch colors here. Okay. What we were doing in the table was we picked values that were a little bit away from the value that we wanted to. So I've chosen an x value here that is a little bit less than x equals 2. Then we evaluated our function. Okay? So the value of our function at whatever that x value is that I've chosen would be right here. So all of our values of f at x have to be points on this curve here. And if we imagine moving this closer and closer, our x value closer and closer to 2, it's like we're moving along this curve towards this point here where the graph of our function sort of meets that line coming down from x equals 2. So as we move along this curve, from here along like this, what value of y, or what value of f at x, do we seem to be heading towards? What value of y will we get to when we actually get to x equals 2? I hear you saying -2, and then wondering, is it really that easy? Yes, it is that easy. Okay? -2. Okay? Now, to make sure of this, we should think about what's going to happen if we approach from the other side. So if we were to pick a value of x that was larger, okay, we would end up starting up here, and we would imagine as we move this x value closer and closer along this curve, we're going to go like this, and we're going to be tending, again, this curve is kind of coming down like this, tending closer and closer to this value of -2. So the limit as x tends to 2 of 1/2 x squared minus 4 is -2. And in this case, we could just evaluate our function at -2, and that would give us the same answer. F at -2 would be 1/2 -2 squared minus 4, which is -2. So let's look at a slightly trickier graph here. This is the graph of the function f at x equals x squared, x plus 2 divided by x squared minus 4. Rational function, we've got two branches here. And we want to evaluate two limits here. First one is going to be the limit as x tends to -2 of our function. So we want to find x equals -2, and we see that there is a nice, the function actually exists. There's a point on the function that corresponds to x equals -2. And then we just sort of verify. if we imagine starting on sort of the left-hand side and moving that way, or if we imagine starting on the right-hand side and moving that way, does our curve, do the points that make up our function seem to all be heading towards the same value? Yeah, those two like blue arrows are going to converge right on that point there that is on our function at x equals -2. So we can just read off that value from the graph. And that's going to be -1/2. This is really just the y value from the graph. In this case. The next limit we want to take a look at is the limit as x tends to +2 of our function. So we find, let's do this one in green here, we find x equals +2. Okay? And if we go sort of a little to the left, we find where we are on the graph of our function, and we sort of start heading towards +2, we're moving along our graph like this. If we go to larger values, or from the right, we find a point on our function, we start moving our x value towards +2, we're kind of going to follow along the curve like that. So are those two green arrows that show what our function is doing as we approach +2, are they tending toward the same value? Riley shook his head no. Is that right, Riley? They are heading way off in different directions. So there isn't a consistent value that this function is heading towards as we get closer and closer to x equals 2. Okay? So in this case, the limit does not exist. Okay? So we don't have a consistent value we're heading towards, so the limit doesn't exist. So these are our possibles. It can tend towards a specific value, or sometimes we don't have a limit that exists. Okay. So our final question. We've got one complicated graph here. We want to evaluate the limits for this function. The function is just shown graphically as x tends to the values of 3, 2, 4, 1, and 5. And I'm sure there's a reason why I did them in this particular order. I guess we're going to find it out. Okay, the limit as x tends to 3 of our function. So we look at the graph of our function. What is happening as we tend towards x equals 3? So imagine finding a point on the function onto one side of x equals 3, a point on the other side of x equals 3. Imagine moving towards x equals 3. Are we heading towards a consistent value? What do we think here? Kevin, what do you think? Good. What value are we heading towards? We're heading towards 1, so that limit is going to be 1. What about the limit as x tends to 2 of our function? So now we're over here. Okay. Again, go to one side of x equals 2, the other side of x equals 2, follow the curve along. What do we see is happening as we approach from the left and from the right? What do you think, Carnegie? From the left it goes to 2, and from the right, what is it tending towards? Is it tending towards 2 from the right? It's tending towards 3 from the right. So if it's approaching one number from one direction and a different number from another direction, what do we say about our limit? Does not exist. Beautiful. What's up now? Okay, the limit as x tends to 4. Now that open circle there means that the function doesn't exist at x equals 4. There's no point on the graph there. It's a hole in the graph. Okay? These dark circles here and here mean that there is a point there. So at x equals 4, our function does not exist. Right there. But what happens as we approach x equals 4 from either side? What do we notice here? Alana? It's tending towards a value of 2 on both sides. So our limit is 2, even though our function doesn't actually exist there. X equals 1 is a weird one. The value of our function at x equals 1, so I should write f at 1, is 2. Okay? That's this black dot right up here. But what is the limit as x tends to 1 of this function? If you follow the trends of the curve on either side, what value do these seem to be heading towards, Malcolm? They seem to be heading towards 1. So even though the function has a value of 2, the limit as we tend towards 1 is just 1. Finally, the limit as x tends to 5 of our function, well, what's going on as we approach 5? What's happening, Liam, to our function as we approach x equals 5?
It never hits 5.
It's never going to hit 5. It's going to approach it, but it's just never going to make it there, okay? Because our curve, what is the value of f at x doing? What is it tending towards? If you see it just going down and down and down and never stopping, we would say that it is tending towards almost infinity. Infinity would be going right up, so if it's going down, it's going to negative infinity, right? So we could say that our limit is tending towards negative infinity if we want to, and you will see sometimes you'll see it described as tending towards negative infinity. My personal feeling is that because negative infinity isn't really a number, it can't really be used as a limit. So I would say that this limit does not exist. There's no particular value that this function is tending towards. It's tending in a direction, and that's the direction towards negative infinity. Okay, so I would say it doesn't exist. Right. And that's limits using tables and graphs.